Today we discuss a very special type of relation, which is an equivalence relation. Given a set A and R a relation on A, R is an equivalence relation provided, well, we had these three properties last time. One was reflexive, one was symmetric, and one was transitive. And if you have all three of these, then you have an equivalence relation. Now, what is an example that we saw? Let A be any set. And then we will define R on A as follows. For A, B, and A relates to B if and only if A equals B. We saw this relation at least when A was natural numbers. This, well, what does this say? A relates to B, or two elements are related if and only if they're equal. So you can think about this as being just equality, and this is definitely an equivalence relation. In fact, this consists of ordered pairs, A comma A, for every single A in A. So this relation is this diagonal relation on a set A. Now, it's also the case that all of these ordered pairs, A comma A, in this particular R, are required in order for a relation to be reflexive. So this is kind of an interesting thing to make an observation, is that note any equivalence relation on A contains this relation R as a subset. Any reflexive relation will contain this one, this equality. Now, generally, these equivalence relations, being reflexive, symmetric, transitive, it's really kind of a generalization of equality. So let's see another example now. Here is an example. The set A is the set of all finite subsets of the integers. Elements in A are finite subsets of the integers. And then I define a relation on A where, so this says C and D are both finite subsets of the integers. C relates to D if and only if they have the same cardinality. So notice that C need not equal D. Maybe I will make this comment before we show that R is an equivalence relation. So for example, in this relation, let's see, 1, 2, 3 relates to 4, 5, 6, even though these sets are not equal, but they have the same cardinality. Okay, that's just an example. Now, we will prove this relation is an equivalence relation. Okay, we need to verify reflexive, symmetric, and transitive. So for reflexive, let C be an A, then C is a finite subset of the integers. Very nice. Well then, certainly cardinality of C equals cardinality of C, and this means C relates to C. Now for symmetric, we need two elements of A, and we assume that C relates to D. Well then, the cardinality of C equals cardinality of D. We can just write this the other way and just write it this way. Cardinality of D equals cardinality of C, and this means D relates to C. So far we have reflexive, symmetric, finally transitive. We can take three, maybe C, D, and E with, well, we need C relates to D and D relates to E, and then we must show that C relates to E. Okay, well, we have the cardinality of C equals the cardinality of D, and then this says the cardinality of D equals the cardinality of E. But you see, both cardinality of C and cardinality of E are equal to the same number, namely cardinality of D. So we in fact do have the cardinality of C equals the cardinality of E, which shows that C relates to E. And this is the end. We have proven that this relation is an equivalence relation by showing it's reflexive, symmetric, and transitive. Now for another example, and that is define R on Z as follows. So two integers, x and y, x relates to y, provided x and y have the same parity. Now what does this mean? Well, same parity, this means x and y are both even, or x and y are both odd. This is same parity. Now, we must show this relation is reflexive, symmetric, and transitive. Well, for reflexive, clearly, x has the same parity as x. And this means that x relates to x. Okay, symmetric. We let x and y be in Z with x relates to y. Well then, x and y have the same parity. They're both even or odd. Well, if you just state it the other way, x and y have the same parity, then y and x have the same parity. So we see this is symmetric. Finally, for transitive, we need three integers. Well, let's consider this. Integer y is either even or odd. And this part says that x has the same parity as y. And this part says that z has the same parity as y. Okay, so whatever y is, both x and z are that, whether it's even or odd. Both x and z have the same parity as y, meaning x and z have the same parity. They're both even or odd. And x relates to z. And this is the end of proving that this relation on the integers is an equivalence relation. Now for an important definition, suppose R is an equivalence relation on A, then for A and A, we define the equivalence class. Of A. And this is denoted like this. This class, here's the definition. This is the set of all x in A such that x relates to this little a. So this is a set, it's a set of all elements in capital A that relate to this little a. And here, a is called a representative for this class. Now, let's see, maybe quickly, let's do an example, and then I really want to prove something beautiful about these equivalence classes. If we let R be the same parity as, this is the one that we just worked with on the integers. Well, let's take an integer. What would be the class of 2? We would have 2. Okay, because 2 itself is even, we would have 0. We have 4, 6, 8, 10. Okay, marching forward in that direction, and then we have the negative even integers. Okay, so this is the equivalence class of 2. Now, notice this is also equal to the equivalence class of, say, 6, right? Because what are all of the elements in Z that relate to 6 under same parity as? Well, again, it would just be all of the even integers. You could also, this is the same as the class of 10, for example, or the class of 108. Okay, these are all equal. Writing this versus this versus this, that's just choosing a different representative, right, to list between these brackets. So now that we see this sort of one example of an equivalence class, let's state and prove an important proposition regarding equivalence classes. Let R be an equivalence relation on capital A. Then for A, B, and A, we will prove that A is in its own equivalence class. Two classes are equal if and only if, well, the representatives are related. So the class of A equals the class of B if and only if A relates to B. And then the class of A intersect the class of B is empty if and only if A does not relate to B. This is what we will prove. And then we will make some observations about this proposition. Well, to prove these, we can use that R is an equivalence relation, of course, which means it's reflexive, symmetric, and transitive. So here, for number 1, R is reflexive, which means A relates to A, and this, therefore, A is in the class of A. This was the definition of this equivalence class. It's all elements in A that relate to A. And in particular, since A relates to A is in its own equivalence class. We have proof number 1. I erased the board to give myself more space. You notice if you look at number 2, or similarly, if you look at number 3, these are if and only if proofs. So we will need a little more space. Well, for 2, this is the next one I will prove. First, let's prove this direction. And in this direction, we assume the class of A equals the class of B, and we need to show A relates to B. Well, we've already proven part 1. Which is that A is in the class of A. And since these two are equal, we have that A must be in the class of B. Now the definition of this class was it was all elements in capital A that relate to B. And therefore, we get that A relates to B. That's what I'm trying to prove in this direction. Now for the other direction, we assume that A relates to B, and we need to show the class of A equals the class of B. Now, this is set equality. And we know to show set equality, we must show subset in this direction and then subset in the other direction. So here, we'll do this one first. Let X in the class of A. We need to show X is in the class of B. But we know that X relates to A. That's the definition of this equivalence class. Now also, we are assuming that A relates to B. And so we have that X relates to B. I used here that R is transitive. Right? X relates to A relates to B. Middle ones match, we get X relates to B. And this means that X is in the class of B. Okay? So we have subset in this direction. Now subset here, in this direction. This is very similar. Now, we assume A relates to B. However, we know that R is symmetric. Therefore, B relates to A. And R is transitive. We have X relates to B, B relates to A, means that X relates to A. And we conclude X is in the class of A. Okay? And so this shows subset in this direction. So this ends the proof of 2. And the last one is to prove number 3. Again, you see, number 3, this is an if and only if statement. So let's prove this direction first. We assume the class of A intersect the class of B is empty. And then we need to show that A does not relate to B. Well, if this intersection is empty, then as A is in its own equivalence class, this was number 1, which we proved, we see that A is not in the class of B, right? Because the intersection of these two are empty. And just translating what this means, it means that A does not relate to B. And so this is this direction. Now we just need to prove this direction and we will be done with part 3. And because I am not proving this direction directly, let me label some things. So this is P, this is Q. This direction I am trying to prove Q implies P. Well, let's do this direction by contrapositive. By contrapositive, well, we will assume not P and show not Q. So we assume the class of A intersect the class of B is not equal to the empty set. And then we will show, in fact, we must have that A relates to B. And this will prove this direction. Q implies P using contrapositive. Well, here, this is our assumption. So there exists some X in the class of A intersect the class of B. Now, what does that mean? This means that X is in the class of A, in particular, X relates to A, and X is in the class of B, meaning X relates to B. Now I need to use that R is an equivalence relation, and so I will use that R is both symmetric and transitive. as R is symmetric, I can say A relates to X. And as R is transitive, well, what do we have here? We have A relates to X. We have X relates to B. And we have transitivity. So middle ones match. We would get that A relates to B. And this was what I was trying to prove. Show A relates to B. We have shown it. This is the end of part 3, but also this is the end of this big proposition. But what is this saying? This is what is really important about equivalence classes. Using this proposition, we see, well, there's two things that I want to point out. First of all, that the set A itself is a union of equivalence classes. So this big U here, it says you just take the union over all equivalence classes. We see that from here because, well, each element of each equivalence class is an A. That would give you subset in this direction, but then every element of A is in its own equivalence class, and that would give you subset in this direction. So this is in fact equal. It uses this number 1. But what do number 2 and number 3 say? We also see that the equivalence classes they are either equal or disjoint. Right? They're either equal or they're disjoint. There is no overlap unless the sets happen to be equal themselves, these classes. This leads to the following definition: a partition. This is what I am defining of a set A. This is a collection of, well, we need non-empty, we need pairwise disjoint, sets whose union, I'll put this in blue as well, is all of A. This is what a partition is. Now, you see what this proposition shows, especially making these two observations, is that the equivalence classes form a partition of A. And this is something fantastic about equivalence classes for an equivalence relation. So for example, if we go back, this was the one equivalence class we looked at. This was R is the relation, same parity as on the integers. And we looked at the class of 2. I could have also, as we mentioned, written this as the class of 8 or the class of -4, something like this. This is just my chosen representative. Then we have, let's say, the class of 1. And this would be all of the odd integers. Like this. And similarly, I could have chosen a different representative for this class. It would be fine. But what you see, this is the partition. Here is 2 disjoint sets whose union, they're first of all non-empty, and their union is all of the integers. So this is this partition given by the classes for this particular relation. Now, what's another really, really cool example where we see equivalence classes being something meaningful? We define an equivalence relation on this underlying set, which is Z cross z minus 0. So what this means here is that a, b, c, d are integers, b and d are not equal to 0. And then this ordered pair AB relates to CD if and only if AD equals BC. Now, this is an equivalence relation, and perhaps I will post a worksheet that will walk you through the steps to prove this. But let's just look at an example of some classes, because what I want to talk about is the classes. Well, let's take minus 1, 3. This relates to minus 10, 30, because minus 1 times 30 equals 3 times minus 10. They're both negative 30. Similarly, minus 1, 3 relates to 2 minus 6 as, well, minus 1 times minus 6 equals 2 times 3. And I could continue and list many other things that are related just to this one element, minus 1, 3. But we denote for this equivalence relation, and this is what I wanted to mention. This is something we've thought about this semester. What are the classes? The class of an ordered pair A comma B is written like this, A over B. And now you tell me, what are the equivalence classes? The classes, because look, this would be minus 1 over 3, minus 10 over 30, 2 over negative 6. The classes, equivalence classes of this relation are the rational numbers. And this is one of the most beautiful equivalence relations. Really, rational numbers are equivalence classes of this relation, because we know, for instance, a half equals 2/4 equals 25 over 50, right? We know that because of this relation. That's what that equality is of fractions, really, rational numbers.